Hello and welcome to this video on mathematical ramblings. Today we're going to be looking at summing squares. To be more specific, what the sum of the first z square numbers is. To do that, we're going to start by looking at an anecdote from Gauss where he found an efficient way of adding the first 100 numbers as a child. We're then going to look at how this relates to triangle numbers. Finally, we're then going to use summing notation to show and find an explicit formula for the first z square numbers, for the sum of the first z square numbers. So to start off with, who was Gauss? Well, he was a fairly famous German mathematician and physicist as well. He's most well known for, within mathematics at least, for discoveries in algebra and non-Euclidean geometry. But what we're going to be looking at today is a also somewhat famous anecdote of his. So it's apparently the case that as a schoolboy, he was asked, and his whole class was asked, to sum the first 100 numbers, and the teacher probably thought that this would take quite a while, because manually adding together 100 numbers is going to take a while. However, Gauss realized that there was actually a more efficient way to do this. So if we list the first 100 consecutive numbers in order, what we can do is sum the smallest and biggest first. So if we add 1 and 100, we get to 101. If we then look at the next biggest and next smallest numbers, so 2 and 99, that's going to also sum to 101. If you can see how this pattern is going to continue, so obviously all the way until the central numbers, so 49 plus 52 is also going to add to 101, 50 plus 51 is also going to add 101, so you can see that we're going to have 50 pairs of numbers, all of them are going to add to 101, and because of this, we know that the total value, all we're really doing is reordering all these numbers and putting them into pairs. So if there were 50 pairs of 101, the total value of the sum is going to be 5050. So that's a much more efficient way, and it only really took him like a few seconds to actually work out what the sum of 1 to 100 is. So it's not necessarily difficult to do, but what's difficult is actually coming up with the idea. So it's really impressive, obviously, that he worked this out at such a quite a young age. So we're going to now look at how this can be linked to triangle numbers. So if you don't know what triangle number is, we can say that T1 is equal to 1. So you can represent that as a single triangle. T2 is equal to 1 plus 2. So you can represent that as the same triangle from T1, and then we can add 2 in a new layer below it. T3 is going to be similar, except it's 1 plus 2 plus 3. So we add another third layer with 3 below it. So you can see how this pattern is going to go. And we can write generally that T of n, so the nth triangle number, is equal to 1 plus 2 plus 3 plus 4, blah, 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 all the way up to n minus 1 plus n. So you can also think of that as the sum of the first n consecutive integers starting with 1. What we want to find though, this isn't that useful in terms of definition. If you want to calculate T of n, it's going to take more time for bigger values of n because you're summing numbers. So the question is there a way of writing T of n as f of n, where f of n is an explicit function or formula, rather than the more sort of implicit one we have, which is a sum of numbers? So let's work it out. You can probably see how this relates to Gauss's anecdote. With that, he was working out the sum of the first 100 integers, which is actually just the 100th triangle number. So we should be able to use his method to work out triangle number more generally. But it's not quite as simple as that, because that method will only work if the number is even, because you're splitting it into pairs. If it's odd, we're going to have one number left over, and that complicates things. But let's just start with a case where you're working out the nth triangle number and n is even, so it's in the form of 2m where m is an integer. We can write down in full, obviously, T of n is 1 plus 2 plus 3, all the way till the central numbers, which will be half n plus 1, all the way to n minus 1 plus n. Again, we'll follow a similar principle, so we can find the biggest and smallest numbers, 1 plus n, next biggest and smallest numbers, 2 plus n minus 1, and then all the way to half n plus 1. And you can see that all of these, if you evaluate them, are going to be exactly equal to the same thing, namely 1 plus n. Again, we're going to have n over 2 pairs, and then each pair is equal to 1 plus n, which means that the total value of the nth triangle number will be n over 2 times 1 plus n, also known as, if you rewrite that, multiply out the brackets, then n squared plus n over 2. But this only works or might only work. We haven't shown that this works for odd numbers, we've only shown that this works for even numbers. So we now want to consider that case where n is odd, and that's half the cases, so that is important. So again, we can write out the general sum form of triangle numbers 1 plus 2 plus 3 all the way up to n minus 1 plus n. If we look solely at this part here in orange brackets, you can realize that that's actually equal to t of n minus 1, because t of n minus 1 is the sum of the first n minus 1 integers. And so for that reason, we can actually just replace the bit in the orange bracket with t of n minus 1. Now, why is this useful? If n is odd, then n minus 1 must be even. And that means we already know how to work tn minus 1 out, because we know how to work out the nth triangle number when n is even. It's n squared plus n over 2, and that works for even numbers. So we can actually evaluate this. T of n minus 1 is going to be n minus 1 squared plus n minus 1 all over 2 plus n. We can then simplify, so write n as 2n over 2, and then just sort of manipulate it a bit. We can cancel out plus 2n minus 2n plus 1 minus 1, and we're left with n squared plus n over 2. So what this shows is, for even numbers, the nth triangle number is n squared plus n over 2, and for odd numbers, it's also n squared plus n over 2, and so we can say that t of n is equal to n squared plus n over 2 for all positive integers n. Obviously, you can't really say like t of 1.5, you can't say the 1.5th triangle number, it just doesn't even make sense. But that means that we've actually worked out a explicit form for the triangle numbers. Explicit formula at least. And if we now input 100 for n, we'll see that this is equal to 5050, and that's what we looked at with Gauss and his anecdote at the beginning. So that's quite cool. So what we've actually been doing with triangle numbers is summing. We know that t of n is the sum of the first n integers. But we can also write this in another form, in another notation, and this is known as summing notation. So this symbol that looks a bit like a capital E is actually the Greek letter sigma, the capital of sigma at least, and that denotes summing. The bottom part here, k equals 1, refers to the start value. So you can see that with t of n, we start with a value of 1. The top value refers to the n value, technically known as the upper limit, and that shows that the sum ends with n. And then here the k is the function. The function here is just f of k is equal to k. That means you don't change it. You leave 1 as 1, you leave 2 as 2, you leave n as n. So this here, the sum of k from k equals 1 up to n, is equal to t of n, so it's the triangle number. This is another way of writing the nth triangle number. So now, looking at this with the original aim of the video, which is to work out the sum of the first z square numbers, first we need to write this as a sum, so s of n is equal to 1 squared plus 2 squared plus 3 squared plus 4 squared, blah 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 blah, all the way up to n squared. We can actually write this again. We're starting with a function of 1 and ending with a function of n, so we're going to have the same start values, so same lower limit and upper limit as with t of n with the triangle numbers, but then the function is going to be k squared. As you can see, all of the terms within the sum are squared, so the k must also be squared for the same reason. If you're wondering, this is below here the more general form or value of a sum. So the sum from k equals a up to b of f of k is f of a plus f of a plus 1, all the way to f of b minus 1 plus f of b. But you don't really need to know about that anyway. That's just there if you're interested in the general form of a sum. So now we want to actually start the process of summing the square numbers. We know that the sum of the square numbers is 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to n minus 1 squared plus n squared. We can actually evaluate obviously each of these, and with n minus 1 squared we can expand it to n squared minus 2n plus 1. If you look at the differences between these square numbers, we'll notice a pattern. So between 1 and 4 is 3, between 4 and 9 is 5, and between 9 and 16 is 7. You might notice that obviously these are odd numbers, 3 and 5 and 7. We're increasing 2 each time. Obviously I'm sure you've seen that just from quadratics you have a common difference. But what's interesting here is that obviously this extends all the way. So the final difference, the final first difference is going to be 2n minus 1. And what this allows us to do is write a square number as the sum of the odd numbers. So you can say 1 squared is equal to 1, 2 squared is 1 plus 3, 3 squared is 1 plus 3 plus 5, 4 squared is 1 plus 3 plus 5 plus 7, each time we're going from 3 squared to 4 squared or 4 squared to 5 squared, we're adding another term, which is the next odd number. All the way up to, if we're working out n squared, we can write that as the sum of 1 plus 3 plus 5 plus 7, so all those odd numbers, up until 2n minus 1. Why is this useful? Well, if we write each of these square numbers, which we're summing, as a sum in itself, we can do this. We have 1 plus 4 plus 9 all the way up to n squared. We can replace 1 with just 1, 4 with 1 plus 3, 9 with 1 plus 3 plus 5, and n squared with 1 plus 3 plus 5 plus, etc., all the way until 2n minus 1. So what we've done here is represented each square number as a sum in itself, and you'll notice that all of these sums start with 1. And because every single one starts with 1, we know they're going to be n ones, so we know that part of the sum will be 1 lots of n, and minus 0 there just makes it simpler later on. If we then look at the next term, 3 is in every single one of these terms, except for the first one because it's the second term in that sum. So it's going to be 3 lots of n minus 1. You can probably see how this will continue. 5 is in every single one of these square brackets except for the first 2, so it's 5 times n minus 2, all the way until 2n minus 1, in which there's only 1. And we're going to do something slightly weird. We're going to rewrite 1 as n minus 1. That's just because then we'll have minus all the way, and you'll see on the next slide why this is important. Okay, so with the part that we just got from the previous slide, what we can do is you can multiply out the brackets and then factorize into the terms that contain n, so these ones, and that is 1n plus 3n plus 5n all the way till 2n minus 1 brackets n, and if we factorize, we'll get that that part sums to n lots of 1 plus 3 plus 5 all the way up to 2n minus 1. But 1 plus 3 plus 5 plus 2n minus 1 is exactly what we saw in the previous slide for the representation of n squared, so it'll be easy to actually evaluate that in a moment. We can then look at the terms that don't contain n, and that's these. So we have 1 lots of 0 plus 3 lots of 1 plus 5 lots of 2, all the way up till 2n minus 1 times n minus 1. So we can then say that the sum of the square numbers, because that's all the way from the beginning, we're keeping that being equal to the sum of the square numbers, is equal to n lots of the sum of 2k minus 1, which we know actually knows to be n squared, but we'll evaluate that fully in a moment, minus the sum of 2k minus 1 times k minus 1. Why is this? Well, if we actually look at the sum highlighted in green above, we have 1 lots of 0 plus 3 lots of 1 plus 5 lots of 2. If we focus on the left side, so the part outside the brackets, we have 1, then 3, then 5. That's again just the odd numbers, so 2k minus 1. If you look at the part inside the brackets, so the 0, the 1, the 2, all the way up to n minus 1, that's just the first integers, but starting with 0 instead of 1, so it'll be k minus 1. Can then do is, because we know that the sum of 2k minus 1, which we saw from the previous slide, the sum of the first odd numbers, the sum of the first n odd numbers is n squared. We can then replace the sum of 2k minus 1 with n squared, so we have n lots of n squared, and then we can expand 2k minus 1, k minus 1, so there's brackets, to get the sum of 2k squared minus 3k plus 1. We can then evaluate n squared, that's just going to be n cubed, and we can split this sum, the sum of 2k squared minus 3k plus 1, into separate sums, so minus the sum of 2k squared plus the sum of 3k minus the sum of 1, and do it again with n cubed minus 2 lots of the sum of k squared plus 3 lots of the sum of k plus the sum of 1. So that's just going to make it really simple to actually evaluate this. So what we're now left with is that the sum of k squared, which is what we're looking for, is equal to n cubed minus 2 lots of the sum of k squared plus 3 lots of the sum of k and minus 1 lot of the sum of 1. And you might notice from that the sum of k squared is on both the left and the right, and the sum of k squared is equivalent to the unknown in equation. It's what we're looking for. So for that reason, we want to move the minus 2k squared on the right over to the left, so we can do that. And we're then left with 3 lots of the sum of k squared. And on the right, we're left with this being equal to n cubed plus 3 lots of the sum of k minus the sum of 1. We know we can evaluate this. Obviously, n cubed is going to stay exactly the same, But we can also evaluate the sum of k, because that's actually just the same as the nth triangle number as t of n. It's just n squared plus n. So if we have 3 lots of the sum of k, that's going to be 3n squared plus 3n all over 2. As for the sum of 1, that's just going to be equal to n, because we're adding 1 to itself, n times, because we're summing from 1 to n with a limit and with a sum. So we can just take away n for that. And now we can simplify and collect terms, and we're left with n cubed plus 1.5n squared plus half n, that being equal to 3 lots of the sum we're trying to work out. If we divide by 3 on both sides, we're left with n cubed plus 1.5n squared plus 0.5n all over 3. And simplifying, we're actually finally left with 2n cubed plus 3n squared plus n all over 6. So now, after this whole process, we've managed to work out what the sum of the first n square numbers is. So obviously that's the sum 1 squared and 2 squared and 3 squared and 4 squared all the way up to n squared. And we've worked out a explicit formula for that doesn't involve summing, which is 2n cubed plus 3n squared plus n over 6. And what's particularly interesting is that this process that we followed can be repeated for higher powers. So for cubed numbers, you could work out the sum of the first n cubed numbers, and then numbers to the 4, numbers to the 5, numbers to the 6. Any positive integer we can work out using a very similar process. So, thank you for watching. Please like, comment, and if you enjoyed this, please subscribe. It really helps out. And then you'll be notified of any future content that I release. I've got some interesting stuff planned, but you'll have to wait and see what exactly that will be. So thank you for watching. Like, comment, and subscribe. Have a great day, and bye-bye.